Every hobby, every industry, every corner of human knowledge accumulates myths that refuse to die no matter how many times experts debunk them. Railroad history is worse than most because it combines nostalgia, mechanical complexity, and generations of enthusiasts repeating things they heard from other enthusiasts who heard them from someone who once stood near a train. The result is a body of conventional wisdom so riddled with errors that separating fact from fiction requires burning down almost everything you think you know. These aren't obscure technical disagreements between engineers arguing over valve timing. These are fundamental misconceptions that millions of people repeat with absolute confidence while being absolutely wrong. 20 locomotive myths that have survived decades of debunking, and if you still believe any of them, it's time to update your understanding. Myth number 1. Steam locomotives were inefficient machines that deserved to be replaced by diesels. This is the foundational myth of railroad history, and it's dramatically oversimplified. The claim that steam locomotives operated at 6 to 8% thermal efficiency, while diesels achieved 25 to 30%, gets repeated in every railroad history book. The numbers aren't wrong. The conclusion is, thermal efficiency measures how much fuel energy gets converted to work at the drawbar. By that narrow metric, diesel wins. But thermal efficiency ignores everything else. Steam locomotives burned coal, which in the 1940s cost roughly 1/5 as much as diesel fuel per unit of energy. A steam locomotive at 7% efficiency burning cheap coal could move freight at lower fuel cost per ton-mile than a diesel at 28% efficiency burning expensive fuel. Railroads didn't switch to diesel because diesel was more efficient. They switched because diesel reduced labor costs. A diesel could be operated by a smaller crew, didn't require water stops or ash disposal, and could run continuously without hours of preparation. The savings came from eliminating infrastructure and labor, not from thermodynamic superiority. Norfolk and Western proved this. They ran modern steam alongside diesel, and the steam held its own on cost until the support infrastructure was deliberately dismantled. The myth persists because bigger efficiency number equals better. Modern analysis by historians like Eugene Huddleston has shown that well-maintained steam operations on railroads with cheap coal access were economically competitive with diesel well into the 1960s. The myth persists because it's simple. Bigger efficiency number equals better. Reality is far more complicated. Myth number 2. Bigger locomotives are always more powerful. This one seems so obvious that questioning it feels absurd. A big boy must be more powerful than a small switcher. In terms of raw horsepower, certainly. But horsepower isn't power in any useful railroad sense. What matters is tractive effort, the actual force applied to moving a train, and tractive effort is determined by weight on drivers and adhesion, not by how much steam or diesel power the prime mover produces. A small, heavy switching locomotive with all its weight on driving wheels can exert more starting tractive effort than a much larger locomotive with weight distributed across unpowered carrying wheels. Union Pacific's big boys produced approximately 135,000 pounds of starting tractive effort. A much smaller and lighter 2-unit diesel set of the same era could match or exceed that figure because diesel-electric transmission converts engine power to tractive effort more efficiently at low speeds. The big boy's massive boiler and firebox were necessary to sustain power at speed, not to produce maximum starting force. Size determines sustained power output. Weight on drivers determines starting force. They're completely different characteristics, and confusing them leads to nonsensical comparisons. The myth survives because big locomotives look powerful, and human brains equate size with strength. Physics doesn't care what looks impressive. Myth number 3. Diesel locomotives replaced steam because they were more reliable. Early diesel locomotives were spectacularly unreliable. First-generation EMDF units suffered chronic traction motor failures and electrical faults. Alco diesels were worse. Their 244 engine was so prone to failure that railroads joked about buying them in pairs so one could tow the other home. Baldwin diesels were catastrophic. What diesel offered wasn't reliability, it was availability. A diesel that broke down could be repaired in hours or days. A steam locomotive might need weeks in a back shop. Diesel's advantage was that failures were resolved faster and didn't require specialized infrastructure. A steam locomotive needing a tube replacement required overhead cranes and boilermaker expertise. A diesel needing a traction motor swap needed a drop table and an electrician. Additionally, a failed diesel unit could be cut from a consist, and the remaining units could continue. A failed steam locomotive was dead weight, dragged off the main line. The maintenance infrastructure was simpler, not the locomotive. This operational flexibility is what killed steam, not some mythical reliability advantage that first-generation diesels absolutely did not possess. Myth number 4. The Pennsylvania Railroad's T1 was a terrible locomotive. This myth is so embedded in railroad lore that challenging it produces genuine anger. The T1 had problems. Wheel slip was severe. Maintenance was expensive. The poppet valve gear was complex. But terrible? The T1 routinely sustained speeds above 100 miles per hour in revenue service. It produced more horsepower per ton of locomotive weight than virtually any other American steam design. Test results showed thermal efficiency approaching 10%, well above average for steam. The T1's problems were real but solvable. The wheel slip issue was primarily an adhesion problem from the duplex drive arrangement. Modern analysis suggests automatic slip control systems could have dramatically reduced this. The poppet valve gear needed refinement, not abandonment. Franklin Railway Supply was actively improving the design when PRR pulled the plug. The T1 was killed by timing, not fundamental design failure. PRR committed to dieselization before the T1's problems could be addressed. Given another 5 years, the T1 might have become one of the greatest American locomotives ever built. PRR scrapped every T1 and preserved none, which tells you more about corporate embarrassment than engineering failure. Myth number 5. Electric locomotives are always more efficient than diesel. An electric locomotive converts electrical energy to motion at 90 to 95% efficiency at the wheel. Impressive. But where did that electricity come from? If it came from a coal-fired plant at 33% efficiency, transmitted through power lines losing 7%, stepped through transformers losing another 2%, the total well-to-wheel efficiency might be 25%. A modern diesel achieves 30 to 35% well-to-wheel because fuel is burned on the locomotive with no transmission losses. Electric wins only when electricity comes from efficient sources like hydroelectric or nuclear. On a railroad powered by coal-fired electricity, diesel can be more efficient from a total energy perspective. Railroads that electrified with cheap hydro made brilliant decisions. Railroads that electrified with coal-fired electricity sometimes achieved marginal or negative efficiency gains. The myth persists because people compare locomotive efficiency in isolation rather than system efficiency from fuel source to wheel. Blanket statements about electric superiority are oversimplified. Myth number 6. Train wheels are cone-shaped to keep trains on the track. This gets taught in physics classes worldwide, and it's so incomplete that it creates a fundamental, misunderstanding. Yes, train wheels have a conical profile that provides centering tendency through curves. But if conicity were the primary guidance mechanism, trains would derail constantly because the centering force is extremely weak at speed. What actually keeps trains on track is the flange. That vertical lip on the inside edge provides a hard physical barrier preventing lateral displacement. The conical profile provides gentle self-centering during normal straight running. The flange provides emergency guidance during sharp curves, switches, and any condition where lateral forces exceed the profile's centering ability. Engineers who design rail vehicles spend enormous effort on flange profile optimization because they know it's the actual safety-critical mechanism. On most tangent track, a well-maintained wheel set's flanges never touch the rail. The conical action handles everything. But in curves, during hunting oscillation and during switch negotiation, flanges do the critical work. The myth gives people a dangerously incomplete understanding of a system where getting it wrong means derailment. Myth number 7. Steam locomotives exploded frequently and were inherently dangerous. Victorian-era boiler explosions burned into public consciousness so deeply that people still associate steam with catastrophic failure. In reality, boiler explosions on properly maintained locomotives were extraordinarily rare by the early 20th century. Alco and Baldwin collectively built over 100,000 steam locomotives. The number suffering genuine boiler explosions in the 20th century can be counted in dozens. Federal boiler inspection laws passed in 1911 reduced explosions to statistical insignificance. By the 1940s, a passenger was far more likely to die in a grade crossing collision than a boiler explosion. The perception came from survivorship bias. An explosion is dramatic and memorable. Tens of thousands of locomotives operating without incident don't generate stories. A single explosion produces headlines reprinted for a century. Meanwhile, diesel locomotive fires from fuel system failures and electrical faults rarely make headlines because they lack dramatic visual impact. Modern diesels carry 5,000 gallons of flammable fuel at lethal voltages. They're not inherently safer than a well-maintained steam boiler. They're just differently dangerous in ways that don't capture public imagination. Myth number 8. Maglev trains are the future of rail transportation. This has been the future for 50 years because the economics never work. The technology functions perfectly. Trains float on magnetic fields and achieve remarkable speeds. The Shanghai Maglev has operated commercially since 2004 at 430 kilometers per hour. It's also catastrophically expensive and fundamentally incompatible with existing rail networks. A Maglev line requires entirely new infrastructure. New guideway, new stations, new maintenance facilities, new power supply. Nothing from the conventional network can be reused. Every kilometer costs 5 to 10 times what conventional high-speed rail costs. Japan's Choshinkansen Maglev is projected at over $300 million per kilometer. For that investment, you could build conventional high-speed rail at 300 kilometers per hour connected to the existing network. Maglev creates isolated corridors. Conventional rail creates networks. Networks are exponentially more valuable because they connect everything to everything. Every Maglev proposal has either been cancelled, built as a short showcase that can't cover expenses, or is under construction with ballooning budgets. The technology works, the economics don't. And they never will as long as conventional high-speed rail offers 85% of the speed at 15% of the cost. Myth number 9. Railroad gauges were determined by the width of Roman chariot wheels. This myth is so persistent that it has its own Snopes page. The story claims that standard gauge of 4 feet 8.5 inches traces back through English road ruts to Roman chariots. It's complete nonsense. George Stephenson chose that gauge for the Stockton and Darlington Railway in 1825, based on the existing gauge of coal tramways in northeast England. Those tramways used various gauges, and Stephenson selected one that was common in the mines where he worked. The gauge has no connection whatsoever to Roman chariots, Roman roads, or Roman anything. Roman chariots varied in width. Roman roads didn't have standardized ruts. The entire premise fails at every factual checkpoint. The story persists because it's a satisfying narrative about how ancient decisions constrain modern technology. Humans love stories about path dependence. This particular story just happens to be fabricated. The real history of gauge selection is far more interesting. Different engineers chose different gauges based on local conditions, available equipment, and personal preference. The gauge wars of the 19th century involved genuine technical debates about optimal track width. Isambard Kingdom Brunel's 7-foot broad gauge offered real performance advantages. Standard gauge won not through technical superiority, but through network effects. More track existed in standard gauge, making it the practical choice regardless of engineering merit. That's a genuinely interesting story about technology adoption. The Roman chariot myth replaces it with fiction. Myth number 10. Trains can't go uphill. Nobody believes trains literally can't climb grades, but the myth that steel wheels on steel rails can't generate enough traction for significant grades is surprisingly widespread. People cite the low friction coefficient, roughly 0.25 to 0.35, and conclude trains are limited to flat terrain. This misunderstands how friction and grades interact. A friction coefficient of 0.30 means a locomotive can exert tractive force equal to 30% of its weight on drivers. A 200-ton locomotive generates approximately 60 tons of tractive force. A 2% grade requires roughly 20 pounds per ton of train weight to overcome gravity. For a 5,000-ton train, that's 50 tons of resistance. Our locomotive handles that with force to spare. Conventional railroads routinely operate on 2 to 3% grades. Helper districts handle 4%. Rack railways climb 48%. The Pilatus Railway in Switzerland has operated safely at 48% since 1889. The low friction is actually an advantage on level track, where it means minimal rolling resistance. Trains sacrifice hill climbing for level track efficiency. Exactly the right trade-off for a transportation system built on carefully graded rights of way. Myth number 11. Cow catchers were designed to save cows. The pilot, which is the correct term for what people call a cow catcher, was designed to save the train, not the animal. When a locomotive strikes a large animal at speed, the critical danger is the animal going under the wheels and derailing the locomotive. The pilot's purpose is to deflect the animal to the side, clearing it from the path of the wheels. It's not a humanitarian device, it's an engineering solution to a derailment hazard. Early railroad lines ran through open range with no fencing. Animal strikes were extremely common, sometimes occurring daily on certain routes. Without a pilot, a large animal going beneath the driving wheels could lift the locomotive off the rails. Derailments from animal strikes caused fatalities among crew and passengers. The pilot was developed as a life safety device for humans that incidentally reduced animal casualties by deflecting rather than running over them. Modern locomotives still carry pilots, though they're now styled as integral parts of the car body. The function remains identical. Federal Railroad Administration regulations require that locomotives be equipped with pilots specifically to prevent derailment from track obstructions, not to protect livestock. The myth persists because cowcatcher is a friendlier term that implies concern for animals. The reality is purely mechanical. The pilot saves the train. What happens to the cow is secondary. Myth number 12. Diesel locomotives are powered by diesel fuel directly driving the wheels. Most people assume diesel locomotives work like trucks, with the engine connected through a transmission to the wheels. In reality, most are diesel-electric machines where the engine drives a generator producing electricity for traction motors on the axles. The engine never directly moves the train. It's an onboard power plant. This explains why diesel locomotives behave differently from trucks. A truck can stall by overloading the drivetrain. A diesel-electric cannot, because there's no mechanical connection between engine and wheels. If resistance exceeds what traction motors can overcome, the motors draw more current, loading the generator, loading the engine, which responds by consuming more fuel. This is also why diesel locomotives don't have gear shifts. The electrical transmission provides infinite ratio variation automatically. At start, Motors produce maximum torque at low speed. As speed increases, motors trade torque for speed through natural electrical characteristics. There are diesel hydraulic locomotives that use fluid coupling instead of electrical transmission, but they're relatively rare. The myth matters because it leads people to fundamentally misunderstand how these machines operate and why they behave the way they do. Myth number 13. High-speed trains are impractical in America because the country is too big. This myth combines geographic ignorance with motivated reasoning from aviation and highway lobbies. America is big. Nobody disputes that. But the relevant comparison isn't New York to Los Angeles. It's city pairs within 300 to 600 mile ranges, where high-speed rail outcompetes both driving and flying when total journey time is considered. The Northeast corridor from Boston to Washington is 457 miles. Paris to Marseille is 482 miles. Tokyo to Osaka is 320 miles. These are proven, profitable high-speed rail corridors with comparable distances to dozens of American city pairs. Dallas to Houston is 240 miles. Los Angeles to San Francisco is 380 miles. Chicago to St. Louis is 300 miles. Atlanta to Charlotte is 240 miles. None of these distances are too big for high-speed rail. They're in the sweet spot where rail dominates because it offers city center to city center travel without the time overhead of airport security, boarding, and ground transportation at both ends. The myth serves people who don't want high-speed rail built for reasons having nothing to do with geography. Highway construction interests, airline interests, and political ideologies opposed to public infrastructure investment all benefit from the too big narrative. Japan is smaller than California. France is smaller than Texas. Both countries built high-speed rail networks that transformed their economies. Japan is smaller than California. France is smaller than Texas. Both built high-speed networks that transformed their economies. America isn't too big for high-speed rail. It lacks the political will, not the geography. Myth number 14. Steam locomotives require enormous amounts of water and therefore can't operate in deserts. Railroads crossed every major desert using steam. Southern Pacific operated across the Mojave and Sonoran for decades. The Hejaz Railway ran through the Arabian Desert. Australian railroads crossed the Nullarbor Plain. The solution was universal. Carry enough water or provide it along the route. Desert railroads built water facilities using wells, pipelines, and water trains. Some used condensing tenders that captured exhaust steam and returned it to the boiler. South African railways developed condensing locomotives running 700 miles between water stops. The infrastructure existed and worked. Union Pacific operated water trains across Nevada long before diesel arrived. The claim that steam can't operate in arid environments is contradicted by a century of operational history across 6 continents. The myth confuses inconvenience with impossibility. Modern diesel locomotives require fuel delivery infrastructure that's equally expensive. Nobody claims diesels can't operate in deserts because they need fuel stops. Myth number 15. The Golden Spike ceremony at Promontory Summit in 1869 completed the first transcontinental railroad. The ceremony celebrated the meeting of the Central Pacific and Union Pacific and was genuinely historic. But passengers and freight couldn't travel coast to coast on a single rail line. The Union Pacific's eastern terminus was Council Bluffs, Iowa. The nearest connection was across the Missouri River in Omaha, but there was no bridge. Passengers had to be ferried across, transferred to a different railroad, and continue on a patchwork of connecting lines. A continuous transcontinental railroad never existed. Coast-to-coast travel required multiple transfers between different railroads on different schedules. The Golden Spike was brilliant public relations, but it represented one link in a chain, not a completed system. The myth matters because it simplifies a complex achievement into a single dramatic moment. obscuring the enormous ongoing effort required to create a functioning transcontinental transportation network. Myth number 16. Railroad tracks expand in heat and contract in cold, requiring expansion gaps. This was true for jointed rail and is still visible on older tracks. The clickety-clack sound comes from wheels crossing these joints. But most modern main-line track is continuously welded rail with no joints. CWR is laid at a specific temperature and stressed to prevent buckling or pulling apart. The rail is restrained by ties, ballast, and anchors that prevent longitudinal movement. The steel still wants to expand and contract. It just can't, because restraining forces exceed thermal forces. When CWR fails, the result is dramatic. Heat-induced sun kinks can derail trains. Cold-induced fractures cause separation. But these failures are rare on properly maintained track. The myth persists because jointed rail was universal within living memory. Modern welded rail is silent and invisible, so people don't realize the expansion gap problem was solved decades ago. The vast majority of CWR operates without incident through temperature ranges exceeding 100 degrees Fahrenheit between summer and winter extremes. Myth number 17. Trains are obsolete technology being replaced by trucks and autonomous vehicles. Global rail freight tonnage has increased in almost every decade since World War II. American Class I railroads move approximately 40% of all intercity freight ton miles, more than any other mode. Rail freight efficiency has improved dramatically. Modern railroads move 1 ton of freight 500 miles on a single gallon of diesel fuel. No truck can approach that efficiency. The physics are unbeatable. Steel wheels on steel rails produce roughly 1/10 the rolling resistance of rubber tires on pavement. A single locomotive replaces 300 or more trucks on the highway. Autonomous trucks will improve highway efficiency, but cannot change the fundamental physics of rubber-on-asphalt rolling resistance. A self-driving truck still requires 10 times more fuel per ton-mile than a train. Passenger rail ridership has also increased globally. Europe, Asia, and parts of Africa and South America are building new rail lines, not abandoning them. American passenger rail suffers from deliberate policy neglect, not technological obsolescence. Countries that invest in passenger rail see ridership growth that routinely exceeds projections. The myth that trains are obsolete serves specific economic interests. Myth number 19. American railroads were built by the government and given free land. The federal government granted land to some railroads, primarily transcontinental lines in the 1860s and 1870s. What gets omitted is the conditions. Land-grant railroads transported government freight and military personnel at 50% of commercial rates for decades. The Government Accountability Office calculated that by 1946, the government had received services valued at far more than the original grants. The railroads paid through decades of discounted service. Additionally, over 90% of railroad mileage was built with private capital. The Great Eastern Railroads received no federal land. The land grant program applied primarily to Western railroads through unsettled territory. The myth that railroads were government-subsidized enterprises built on free land misrepresents a limited program as universal policy and ignores the substantial payback that occurred through reduced transportation rates over nearly a century of service. Myth number 20. Modern trains are better than old trains in every way. This is the myth that encompasses all other myths because it assumes technological progress is linear and universal. Modern trains are better in some specific ways. They're safer due to positive train control, crash energy management, and improved signaling. They produce fewer local emissions. They're quieter. They offer better passenger amenities, but better in every way. Modern diesel locomotives have shorter service lives than steam predecessors. A well-maintained steam locomotive routinely served 40 to 50 years. Modern diesels are typically retired after 20 to 25 years because electronic components become obsolete and manufacturer support ends. Modern locomotives are less repairable. A steam locomotive could be rebuilt almost indefinitely because its components were simple mechanical parts that any competent shop could fabricate. Modern locomotives contain proprietary electronic systems that only the manufacturer can service, creating dependency relationships that would have appalled earlier generations of railroad mechanical officers. Modern trains are more complex and therefore more vulnerable to cascading failures. A single software glitch can disable an entire locomotive. Steam locomotives had no software. They failed mechanically in ways that could be diagnosed by looking, listening, and touching. Modern passenger trains prioritize speed over experience. A 1940s streamlined passenger train offered dining car meals prepared by onboard chefs, observation lounges with panoramic windows, sleeping accommodations with genuine privacy, and a travel experience that was an event in itself. Modern high-speed trains offer airplane-style seats, overhead bins, and a vending machine. The journey has been optimized for time at the expense of everything that made train travel worth choosing. Progress isn't always progressive. Modern passenger trains prioritize speed over experience. A 1940s streamliner offered dining car meals from onboard chefs, observation lounges with panoramic windows, and sleeping accommodations with genuine privacy. Modern high-speed trains offer airplane seats, overhead bins, and a vending machine. The journey has been optimized for time at the expense of everything that made train travel worth choosing. Sometimes the old way was better, and pretending otherwise just because it's older is the dumbest myth of all. These 20 myths persist because they're simple, satisfying, and wrong in ways that don't obviously matter until they do. Believing steam was inefficient leads to scrapping valuable heritage infrastructure. Believing Maglev is the future wastes billions while conventional rail starves. Believing America is too big for high-speed rail condemns travelers to congested highways. Myths aren't harmless. They shape decisions, direct investment, and determine which technologies survive. Every myth on this list has cost real money and prevented real progress because someone believed something untrue and acted on it. The cure for myths is evidence, and the evidence is overwhelming. Locomotives and the railroads they serve are among humanity's greatest engineering achievements, and understanding them accurately is the minimum respect they deserve. Don't forget to subscribe so you don't miss future updates. Here's another video I've specially selected for you.